My name is Sam Erickson, and this is my project presentation for ME578. The purpose of this project is to develop a model to predict the material properties and the limitations of lattice structures. Previous research on this topic includes an article published by Noboru Kikuchi and partnering authors who designed a method of optimizing microstructures, such as lattices, to create compliant mechanisms. The motivation for this project is to create a model that will allow more rigid materials to be used in the place of soft, compliant materials by varying only the shape and geometry of the part. This would allow hard plastic materials such as PLA, PETG, nylon, or ABS to be used in the place of closed cell or open cell foams. This could also allow the possibility of designing parts that have varying compliance at different points to be made from a single material by varying only the geometry throughout the part. The inspiration for this project came from my favorite pair of shoes shown in the image on the right. The model parameters used in this study will include the lattice cell pattern, the lattice strut thickness, and the lattice cell size to predict the stiffness, strength, and relative density of the final part. Other parameters such as the lattice coordinate system, type of lattice, or material can be varied but will be consistent for this experiment. The material tested will be PETG, and I will use a Cartesian coordinate system, and the lattices will be planar for the ease of prototyping. This project will follow 20 basic steps, so I will try to move quickly. The first step is to choose 3 basic lattice structures to test. After reading through the previous studies, it is established that the diamond lattice is an optimal candidate for compliance and energy absorption, while the iso-grid triangular lattice is exceptionally rigid. Lastly, the hexagonal lattice will serve as a mid-level candidate. Next, the JMP or JUMP software is used to generate a space-filling design of experiments to adequately cover the design space with a limited number of test samples. 33 test samples were generated across the 3 input parameters. Using the list of design combinations, Altair's Inspire software was used to turn a 20 by 20 mm cube into the necessary lattice structures. However, due to the available version of Inspire, the lattice designs could not be properly exported. The only way to export the files was to wrap the implicit model in a mesh, simplify the mesh, and then do a Boolean intersection between the mesh and another cube. This file could then only be exported as an OBJ or STL. However, the files had over 1 million triangles and were too large to process, even after simplifying. The only available option at this point was to redesign the lattice structure in another CAD program. An API was then created in SOLIDWORKS for each of the 3 lattices. This allowed the design of experiments to be copied over, and the corresponding lattice structures were exported as step files from SOLIDWORKS. Prior to creating physical test structures, the lattice models were validated in an FEA software, which in this case was topology. This verified that the range of lattice parameters would result in the desired behavior to create a reliable model. The designs were 3D printed out of PETG with 100% infill, including the bulk cube. However, due to the limitations of FDM printing, several of the designs were unable to print successfully because they were either too thin or too thick and resulted in improper adhesion to the bed or warping from the bed. In both situations, these extreme design samples were unsuccessful to print even after multiple attempts. The design of experiments, or DOE samples, were measured and the relative density was calculated against the bulk material. After measuring their weight, the samples were loaded one at a time into a 100 kip tensile tester. The tensile tester, being set in compression mode, would press each sample and record the force and displacement, and export the data to a CSV file. While there was a 1 kip and 10 kip tensile tester on campus, they were occupied by research groups during this time, which did result in a lower resolution from using such a large machine. After exporting the data, each CSV file was then processed to convert the inches displaced and the pounds force applied to millimeters and newtons. This data was then used to calculate the stress in megapascals and the strain of the model over time. The graph on the right shows the full stress strain curve of the diamond lattice. The graph increases linearly as the lattice structure behaves like a pseudomaterial until the yield strength of the individual lattice joints are met, after which the structure plastically deforms and creates a new pseudomaterial. This process repeats until the lattice members are in direct contact with each other and the lattice is essentially eliminated, leaving the sample to behave like the bulk material. The graph on the left shows the curve prior to this first yield point. This curve is used to estimate the stiffness and strength of the lattice design. The stress is approximated using 3 methods. First, a visual approximation is taken, then a central difference approximation is taken at 2 points in the linear region, and finally a running average is generated for the duration of the linear region from which the median stiffness is saved. These 3 methods are then averaged to give the Young's modulus of elasticity for the sample. The yield strength is estimated from 0.2% strain offset using the approximate slope of the linear region. This method of measuring the material properties was repeated for all 30 datasets. After entering the results of the compression tests into the DOE table on JUMP, a model of best fit could be created. Two models were created to fit the data, the first being a standard linear regression model. The results of the model are shown here for each of the three outputs, stiffness, strength, and relative density, as determined by the three inputs. The linear regression model demonstrated a strong fit to the model as shown by a high R-squared value as well as a relatively low root mean square error for each output. The second model of fit was a predictive neural model using three levels. Again, this model demonstrated a good fit to the data as shown by the high R-squared values of 0.9936 and 0.9785. However, the sum of squared error values were higher than ideal for each of the three outputs. The formulas for both models were saved, and the relative errors between the predicted and actual values were calculated. Next, a second design of experiments was generated across the original design space to validate the model. In this case, 10 models were generated to fill the design space. However, like before, the samples with the thinnest lattice thickness were failing to be printed. In the end, only 6 of the 10 designs finished printing. The image on the right shows 5 of the 10 designs from one of the repeat print attempts. The validation DOE samples were weighed and the relative densities were calculated. These samples were then subjected to compression testing just as the first samples were. The image on the left shows the sample prior to the compression testing, the image on the middle shows the sample after the test is complete, and the image on the right shows a second, much thicker design for comparison. The results of the second design of experiments were recorded and the datasets were processed in the same manner as mentioned before. The linear regression model and the neural model were applied to the validation study to compare. The image on top shows the linear regression model while the image below shows the neural model. It can be seen that the relative error of the linear regression model is more accurate for some samples, reaching as low as 1% error. However, it also shows the greatest spread with as great as 302% error for another sample. The neural model, by contrast, is less accurate with the best prediction of having only 3% error, but it demonstrates less of a spread with a maximum of only 253% error. It should be noted that both models are significantly more accurate for mid-values such as designs with a 1.6 mm strut thickness, while they get increasingly less accurate towards the extremes. This is likely due to the DOE samples that were unsuccessfully printed and thereby underrepresenting the design space in these extremes. Nevertheless, the models could be used to predict optimal design parameters for a given function. In this case, the design of a sandal should have the target stiffness of approximately 13 megapascals and a yield strength of approximately 1 megapascal. Designs with the optimal stiffness suggest that the lattice pattern would be the diamond lattice to maintain the needed yield strength with a sufficient factor of safety. Of the remaining 5 suitable designs, the 2 best candidates would be either Run 4 or Run 5 because of their decreased weight. Of the 2 options, Run 4 is better because the model has already been validated to predict designs having a strut thickness of 1.6 with the least error. Now the design of the sandal may begin. First, the sandal mentioned previously was scanned using a high-precision LiDAR 3D scanner available in the library. The scans were processed and the model simplified to be using CAD software. The optimal lattice parameters were then applied to the model of the shoe using Alter's Inspire. The chosen design, as mentioned before, is shown in the bottom left. The design explorations show that further modeling would be needed to adapt the lattice design to any manufacturing process. The perimeter would likely need to be connected and the straps would need to be reinforced. Because the final design is unable to be exported from Inspire, the lattice structure was finalized and exported using Topology. The final design was printed using PLA on FDM 3D printer. The model successfully printed using minimal support structures. Comparing the final part to the original shoe, the model maintains all critical geometry and matches the user's foot perfectly. The shoe demonstrates a lower stiffness relative to the bulk material, but the rigidity is still greater than desired. This is likely due to the shell that was added around the lattice structure to make it manufacturable, and subsequently added stiffness that was not anticipated by the model. Overall, the preliminary design can be considered a success. In conclusion, the model was created that accurately predicted the behavior of lattice designs. The model proved a strong correlation between cell pattern, strut thickness, and cell size to the stiffness, strength, and relative density of the part. Expanding this model could map linear relations between the bulk materials and softer, compliant counterparts. Having the relations sufficiently modeled would then allow one to mimic compliant or lightweight materials using only the geometry of the part. As mentioned before, this project was severely limited by the availability of 3D printers, 3D printing capabilities, materials, and tensile testing machines available. In the future, this work should be improved by using better suited machines, a wider range of design parameters, and different materials. Nevertheless, for a preliminary study, the results show significant promise. Thank you.